That's weird. There we go. I would think the video would stop video mute. Everything plugged in. Well, nothing works the same way 2 minutes in a row. All right, good evening, everyone. It's bizarre because there we go. This video is working now. And welcome to yet another episode of Water Systems Design. Today, we're leaving the fast-paced world of stormwater and moving our way down into sewage. That would be more funny in a face-to-face class because they could have creepy pictures. And we're kind of finishing up the semester on sanitary sewers and then tie everything together just before Thanksgiving. To address a question from this morning's class, I'll just address it now. I'm going to manually grade the exams because based on a lot of emails from a lot of y'all, it seems that the server pointed to the wrong input file for the EPA net problem, so the correct answers weren't even available. So I will look over what everybody did and probably manually override almost everything. And that's those things happen. And I was out of town at the time I started getting those emails, and while I could get the emails, there wasn't much I could do to manage the server. So don't worry or lose any sleep about that. Won't be penalizing you for my machine's mistakes. So let's begin today's lesson. So I better share the screen or I'll talk for 20 minutes before someone interrupts me and says you need to share the screen. So today's is lesson 22 on sanitary sewers. And if you were to go to Blackboard, this would be, oh, it wouldn't be your link because I'm in the wrong class yet again. That's better. And let me issue the command twice. Copy, put it into the other section. Browse, lessons. Okay, let's try that again. We'll go to section 1, which is the evening section. That's y'all. And with any luck, yay, there it is. And hopefully this link is still working. So I've been working on it this afternoon. And that does not seem to be the correct lesson. And you can see the network is just blazing fast right now. Okay, that's the right slide for about 2 years ago. I guess we'll go with the local copy. All right, let's begin the discussion. So this is really supposed to be lesson 22, sanitary sewer systems. I'm going to close the chat box, shrink that a little bit, at least on the recording, and it will refuse to accept input because it's... So this comes under the general category of collection systems. And collection systems, or in particular sewers, are used to collect wastewater and stormwater and deliver it to some common location. By common, not in the context of an everyday location, but a single point. In the case of sanitary sewage, that location is usually some kind of treatment facility, and then it leaves the treatment facility and makes its merry way to an outfall to return to the environment, thereby completing the circuit of the mighty water cycle. In stormwater, directly proceeding to an outfall is typical, and passing through a treatment facility for stormwater is uncommon. Not unheard of, but uncommon. Collection systems play an important role in the control of the quality of water. Certainly a sewage system does, because it protects the environment and human health while that sewage is transported to a treatment facility where it can be effectively treated, and then the portion of the water which is reusable is returned to the environment. These systems concentrate certain kinds of non-point discharges and bring them to a single point, and hence they become a point discharge, if you will. And these can be managed quite a bit more efficiently. It's perfectly feasible, for instance, to generate electricity at the single residential level or for a particular neighborhood. But in some context, that's grossly inefficient because then each neighborhood would have to have a stationary power engineer, and you'd run out of people pretty quick. So instead, we collectivize that and use large plants and then just distribute electricity to the point of use. So water and electricity aren't the same thing, but they share some similar properties. You just can't mix them, because since electricity is just compressed fire, when you mix it with water, it explodes out and makes a mess. I know that electricity is not compressed fire. It's just supposed to be some kind of a humor there. Here is a cartoon of Somewhere USA, not our Somewhere USA, but a different Where USA, depicting point and non-point sources. So one of them is identified as a wastewater treatment plant, and presumably it's getting the water from that residence and this city, and they've located this nice city a long way from the wastewater treatment plant. Goes through these different reactors, and eventually it's discharged back into the river, and it's at this point. So that point would be called a point source of discharge. On the right, we have a factory where they make whatever they make in the factory, and its industrial wastewater also comes down a single pipe and discharges at this point. And so those are example of point sources. Point sources in the context of this river. There's some other sources identified here in the drawing. There's all the stormwater from the city or city streets. There's the stormwater that leaves Running Rat Acres subdivision here. There's rural homes out here, and this is showing stormwater leaving the rural homes. And we have cropland where they grow crops. So the leading manufacturer of riding crops comes from this cropland, and an animal feedlot, and the animal poop is collected and makes its way to the river. And the rural homes, cropland, and animal feedlot are treated as non-point sources. And that's because where that water enters the river is somewhere along here, and here it's somewhere along here, and the animal feedlot is somewhere along here. But the precise location at any moment is not well known. So they're distributed over somewhat of a larger area. Now, I maintain that the stormwater coming from our subdivision is likely to be concentrated in a discharge channel and make its way at a known outfall, similarly for the city streets. But I suppose those two aren't guaranteed. So in this diagram, the rural homes, cropland, animal feedlot are identified as non-point sources. Okay, so a simple way to distinguish between the two that's worked for me. Point sources are called that because you can point to them. Non-point sources are called that because you can point at them, but you can't point to them. So that's a usable tongue-in-cheek rule of thumb between point sources and non-point sources. And I guess conceivably these non-point sources, once they make their way to this river, if it discharges into yet another river, then the river itself becomes a point source comprised of a collection of non-point sources. So you can see how confusing it could get, especially if there was a taxable event at each step of the way. Somebody would need to get their payments. So the types of sewers we have are stormwater, which we've examined a little bit already, a sanitary sewer or a separate sanitary sewer, and there's a combined sewer system, which is an old concept, but they're still in use around the world and will likely be for most of your careers, although we wouldn't intentionally be building new combined sewers anymore. They're an important class of open channels. We already know that. They're usually underground, otherwise you trip over them and fall in and you get purple acampucky on your face, and that's bad. They're used to transport wastewater ultimately to its final release point back into the environment. Now the design life of sewers, or the service life, is typically on the order of 50 years. And so in the design, we have to account for the completed conditions and the future conditions that we want our sewer to perform at. I suppose one can effectively argue that that tends to lead to over-design because we can't predict the future, but we can make reasonably educated guesses and at least get our sewer in place and our plans signed, and our invoices out and paid before the sewer fails or we retire. I guess after we retire. So sanitary sewer systems, in these, the individual discharges are collected, concentrated, and delivered to a treatment plant for further processing. Storm sewer systems, the individual discharges are collected, concentrated, and delivered to a receiving water. So those two designations are practically identical with the exception of this intervening treatment plant that gets in the way of the sanitary sewer system. Then a combined sewer system is a sanitary sewer system that's designed to also collect and convey stormwater. So in the past, these were pretty common. New combined systems are no longer built in the United States. You wouldn't be able to obtain necessary permits, and a new one would be in violation of a few Environmental Protection Agency water quality regulations. But in older cities in the US that were comparatively large in the 1880s, by comparatively large, 30,000 residents or more, represent the remaining combined systems in the US. And I'm about to show a map of them, a very blurry map. And in these cases, the black dots represent known combined sewer systems. So the ones here in, see what's north of Florida, that's got to be, let's see, North Carolina, South, this is Georgia. So North Carolina, I get these all mixed up. I think either that one or that one is, oh, this is Atlanta. Don't know which one this is, and I think this is Savannah. So there's 3 in Georgia. There's one here in North Carolina, another one here in North Carolina. And then you get to the northeastern United States, and there's a bunch of combined sewers there. Our friends, New York, Philadelphia, Massachusetts, they all have them. And as you get here to the west of the Appalachians, there's still quite a bit. And then in the Ohio and Mississippi River Valley, in the Midwestern part of the United States, there's still quite a few combined sewer systems around. And then we have the middle part. So this was the large unsettled US, where water itself was hard to find, let alone have a sewer to throw it away in. And then we get out to the West Coast, San Francisco, Sacramento. This is Oregon. Portland is somewhere in here. And you have the Seattle, Tacoma area up here. So the Pacific Northwest, the Atlantic Northeast, and the Mississippi and Ohio River valleys are the last remaining combined sewer systems in the United States. And these generally are in relatively old cities. And the reason they haven't been entirely replaced is it's simply not cost effective. Imagine San Francisco, if you will, having to tear up the entire city of San Francisco to replace a sewer probably isn't a very good idea. So it hasn't happened. And the way these are going to slowly fade away from use in your careers is as projects are done in these particular communities, sewer projects or stormwater projects, portions of the combined sewer system will be removed as part of the project. And so over time, these black dots will slowly disappear. But in the meantime, we have to be cognizant of them because hydraulically they behave as a stormwater system that kind of conveys sewage from time to, well, all the time, plus some stormwater. So we have some added bonus features there of having to manage stormwater as well as having to get these things to go through a treatment plant. And the real challenge, the hydraulics of that is not going to be all that hard unless you're out of a pipe. But the challenge is we design our treatment plants for, say, 100,000 people that are eating food and creating wastewater. And then all of a sudden we have this huge stormwater flow that comes into the plant. So we now have to design a sewage treatment plant that deals with ordinary flows and then huge storm flows. It's certainly not going to be cost efficient to apply the same total treatment process to stormwater mixed with sewage than it is concentrated sewage. So it's a very challenging and really good job security if you're interested in that kind of stuff. So the categories, whether it's storm sewer or sanitary, share similar hydraulics, namely that of open channel flow. and they're topologically similar. They're comprised of pipes, boxes, junctions, and lift stations. So sanitary sewer systems don't have inlets in the same context that storm sewer does, but everything else, it has all the other pieces. So most of the design principles are essentially interchangeable, although the sewer's ultimate purposes are different. Purpose of the sanitary sewer system is to protect public health by isolating wastes from the environment until said wastes can be treated and the reclaimed water released. So this word reclaimed water, when you see that in the context of civil engineering, it mostly likely means the water that is reclaimed from the wastewater stream. And it's not the water that was reclaimed because somebody took your water bottle and walked out of the conference room with it, and you caught them in the hallway, slide tackled them, and got your water bottle back. That would indeed be reclaimed water, but whole different context. And then what's left from the reclaimed water is called wastewater residuals, and then that has to be dealt with in other ways. The storm system is to protect public health by removing nuisance flooding and keeping infrastructure serviceable during all but the worst imaginable weather. And over the last 2 decades, storm sewer systems have been called upon to confer water quality benefit because they serve as the collectors that capture a lot of non-point pollution. So our storm sewer systems are, for most practical purposes, capture some of the non-point sources here. And as such, there's an expectation that that water be dealt with in such a way as to confer some water quality benefit, improve the quality of the water. And we looked at one possible technology unintentionally. I mean, it's not why you were looking at it, but detention basins are one of many tools that are used to accomplish this water quality enhancement act. So sanitary sewers themselves are simply pipeline systems underground that collect and transmit sewage from distributed sources to a central location. Pretty much no different than a stormwater system. The pipes are typically operated as open channels, and that is the pipes are not supposed to flow full, and gravity is the driving force. In general, sanitary sewers are carefully operated so that they do not fill up. That's called surcharging, and in the case of a stormwater system, if a stormwater system surcharges, that's undesirable, but it's not the end of the world. If a sanitary system surcharges, that means you're going to have sewage coming up out of the ground at some point, and you're going to have a lot of splaining to do when that happens. So we design them as best we can so that does not happen. There's portions of the system where the sewage has to be lifted to maintain flow towards the central plant. These locations go by the very cryptic designation of lift station. And sewage on the discharge side of the pump flows in a pipe that is usually called a force main. So when you see the words force main, or you hear a contractor and operator talk about a force main, they usually mean the discharge side of the pump and the portion of the piping on that side that's still pipe under pressure. And in the case of a lift station, that force main might be hundreds of feet long until it discharges into an open channel, which could just be another underground pipe. And then it's just ordinary sewage pipe at that point. The design rules are governed by federal law, state law, and in most cases municipal law. And like the other two water features we've examined, drinking water and stormwater to be precise, these laws and codes are encapsulated in various design documents. We're going to look at specific ones on Thursday, Today I'm just pulling stuff from Texas Administrative Code without citation. So not even I know where it comes from in the code, but I will again by Thursday. These various laws, codes, and guidelines prescribe materials. So what the sewer is supposed to be made out of, the joints, how the pieces of the sewer are connected to one another. It's a little bit more elaborate than the other two systems. The labeling, in fact, there's portions of sanitary systems that have to be correctly labeled, even if they're going to be buried underground again. It seems kind of stupid to put a label on something and then cover it up with soil, but that indeed happens, and there are prescriptions on how the labeling is to be done. And the purpose of the labeling is so that when that pipe has to be dug up again, as the contractors are digging it up, they can tell which pipe they're encountering, whether it's a pressurized water pipe, a force main, and so on. Almost all sewer systems are engineered. And by that, I mean a professional engineer or a licensed design professional is involved up to and at least to the point of stamping their credentials on the design before actual construction occurs. I think for most part that's going to be true of drinking water distribution systems, although there might be a bit of a workaround on that, but because the cost of things drives it outside the lower limit of the dollar value of a project that does not have to be engineered, it's pretty much always going to have to be engineered. So a sewer system that is designed by someone who's not an engineer, who's not under the supervision of the engineer, in theory, at least according to Texas rules, can't be built. Sewage itself behaves essentially as water. It's roughly 5% solids by mass is the upper limit of raw sewage. So if you have a kilogram of raw sewage, then 5% of that might actually be solids. The remainder is essentially water and bacteria and other little creepy crawlers. So it's basically 95% liquid and 5% a combination of floaters, sinkers, and then the dreaded lurker. If we go by volume, the percentage is much smaller. So the solids fraction by volume can be as small as 0.05%. So hydraulically, it's mostly water. It's non-Newtonian, which has some added bonus features once we concentrate the solids in a treatment plant, but that's not the focus of today's discussion. The solids present an interesting challenge because even though they're not a large fraction of sewage, it's flowing day and night. So as long as there's people living 24/7, they'll be producing biosolids, and that goes into the sewage system. And those solids, in some locations, collect. And they would collect because the flow velocities drop below a sufficient velocity to sustain their suspension, or well, pretty much that's why. So here's a picture of cleaning the solids out of a sewer, and this is in Paris, Paris, France, not Paris, Texas. And we have 3 sewer workers underground. This worker here, I want you to keep your eye on him because he's got a pretty special position. So he's scooping up these solids and using a pickaxe for the extra log jammer ones. And then it goes into this bucket, and this guy hands it to this guy, and then it's lifted up. This guy takes it off the crane, hands it to this guy, and this guy pours it into the cart here, and then the cart is hauled off to a Parisian bakery to make mud pie and various other confections for the aristocracy. And there's a barricade located here that presumably is keeping the sewage held back while these three gentlemen can ply their trade. And the way this is drawn, this mound of solids is almost as tall as this sewer worker. So that's kind of disturbing if you think of it. That there's that much solids collected between each cleaning. So just some comments on the pictures. So the comments are supposed to be somewhat humorous, I'm about to make. You'll notice that in the 1800s, the confined entry rules were a little different than they are now. Because in this case, we have 1, 2, 3 people underground, and we have 1, 2, 3 people above ground. This dude here is doing nothing, so that must be a supervisor. This guy's pulling the buckets up, handing them to him. Nowadays, usually it's going to be a quite different distribution. There's usually 3 people above ground for every 1 person underground, and that's so that when the person underground passes out from the stench, the 3 people have enough physical strength to be able to haul them out. And I think the rules are probably a little bit more soundly formulated than that. Now this guy, of all the people in this picture, he's got the best job. You wouldn't think of it. He's underground, it's wet, it's dark. I mean, there's their lantern right there, and it's sewage, so fire and decaying sewage don't necessarily mix well. And he's scooping sewage solids into a bucket. And then he hands the bucket to this guy, and this gentleman hands the bucket to him. The bucket's lifted up, and one of these 2 guys hands the bucket to this guy, who hands the bucket to the back of the cart. And so what this guy has that the other ones in the picture don't have is he doesn't have to take biosolids from anybody. He's the one who's giving everybody the biosolids. Again, in face-to-face, that's actually a funnier joke because I can do a little bit better setup on the presentation. Okay, so back to the present. The characteristics that the design engineer is concerned with is the volume, how much sewage has to be managed, and that will in turn stipulate the size of the pipes and the various other appurtenances that we place into the system in order to deliver that sewage to our collection point. But we're also concerned with its actual quality. Not that we can affect it much, but we're concerned with its corrosion potential. Because the sewage is chemically corrosive, that presents an additional design challenge. So we want to design our systems as best we can to accommodate corrosion and excessive weathering. So using the Texas code as an example, there are specific discussions regarding corrosion and odor. So for example, in the Texas code, corrosion potential is discussed in these following 2 excerpts. If a pipe or an integral structural component of a pipe will deteriorate when subjected to corrosive internal conditions, or if a pipe or component does not have a corrosion-resistant liner installed by the pipe manufacturer, the report, that would be the design report, must demonstrate the structural integrity of a pipe during the minimum 50-year design life cycle. So if we don't explicitly provide piping that's corrosion resistant, we have to demonstrate in a report by some kind of analysis and projection that that pipe will still be there 50 years into the future. Sewage under the right conditions is so corrosive that a 6 or 7 inch wall thickness of reinforced concrete pipe can be degraded and deteriorate in a matter of just a few years, 10 or 12. So that 50-year design life is all of a sudden a long time. Mostly what that's led to is almost uniform specification of corrosion-resistant liners, or where applicable, departure from using reinforced concrete and using high-density polyethylene and various other polymer-based pipes, which at one time we were just guessing that they were corrosive resistant, but we have well over 50 years of practical experience now in their use, that they're generally considered to be pretty effective sewer pipes from the standpoint of corrosion resistance. They're not physically as strong in backfill, so we have other ways to destroy them. And then it also specifically says the pipe must have an appropriate lining if the corrosion analysis indicates that corrosion will reduce the functional life of the pipe to less than 50 years. So the people that wrote this were attorneys. Those were like lawyers, which rhymes with liars. They didn't have the guts to say, use corrosive resistant pipe or use a polymer pipe. They did this way of saying the same thing. There's also odor control. In Texas, an owner shall determine if odor control measures are necessary to prevent a wastewater collection system from becoming a nuisance based upon the potential of the wastewater collection system to generate hydrogen sulfide. Pretty much any wastewater collection system is, by definition, a hydrogen sulfide generator. It's really good at doing that. So the potential odor determination must include the estimated flows immediately following the construction and throughout a system's 50-year expected life cycles. Now, odor control, there's more than one way to control odor. There's expensive ways and some that are less expensive. So in addition to carrying sewage, these pipes also contain air. And with a little bit of creativity, and it's not something that's in any of our textbooks, but if they're designed well, it's possible to get the sewer to actually draw air into it and discharge the air at the treatment plant where you don't care if it stinks. And so basically that moves the odor. There's some other more elaborate schemes involving, I'm going to call her ferric chloride, which is a way of chemically attacking odor. That works. It's not particularly cost effective because now you have an expendable material that has to be supplied all the time. Another technique is to actually use blowers, not leaf blowers that they use to move leaves around in the neighborhood, although that would be a really good use of them, get them all out. Anyway, blah, blah, blah. I'm going on a tangent there. But large industrial blowers to control the airflow and deliver the offensive odors in locations where you can tolerate it. So the last two, both corrosion control and odor control, are somewhat outside the scope of the civil engineering classes that we do here at Texas Tech, or I would dare say at almost any other civil engineering program. And yet there are experts throughout the country and in many firms that have a lot of practical experience in managing these two issues. So when you leave here and go work at a company, you wouldn't be completely left out in the woods. The amount of sewage that we have to manage is essentially estimated the same way as we would with water demand. Small residential service area flows would be estimated based on population or equivalent residential units. And it's a fair bet that the sewage coming out of a residential unit is got to be volumetrically the same as the water going in at the worst case, and then per person contribution to wastewater. Larger service area flows are estimated from land use, anticipated population, and similar nearby measured flows if such measurements exist. Unlike drinking water, which is measured routinely because that's how we issue bills, sewage is not measured routinely. Short-term studies of a couple months are well within the capabilities of any consulting engineering firm. The technologies involved are mag meters, acoustic Doppler profiling, if you can figure a way to keep the toilet paper and other sticky things like that that are in sewage from wrapping itself around the sensor, or install a very low weir in a collection line and measure the water surface elevation and apply a weir equation. Those are all commonly done. The argument against a weir is you're creating an obstruction to flow. And the problem with obstructions to flow is you end up with pictures like this. An obstruction to flow is a place for solids to collect and again possibly create a log jammer in your system. A mag meter is a wire coil that's wrapped around the outside of the pipe, and sewage is slightly conductive, and that can be exploited in a mag meter and can measure flow that way. And acoustic Doppler profiling is probably state of the practice, and the instruments themselves are quite robust. So if as long as you can assure that you have some way of controlling toilet paper, so you don't want to put your profiler right at a lateral where it's bringing in flow from a house, that's a viable tool. These short-term studies would be useful generally during an expansion project, so that you have a really good idea of what the actual flows are. So in Texas, design flows are based on a variety of techniques, and they're provided because the owner must design a wastewater collection system, and the Texas code specifically says to handle the transport of peak dry weather flow, and that's defined in the code, from the service area, plus infiltration and inflow. And we'll get to what infiltration and inflow are shortly. The flow calculations must include the details of the average dry weather flow, the dry weather flow peaking factor, and the infiltration and inflow. And there's tables to provide some of those answers. And it includes the flow expected at completion and at the end of its 50-year service life. Some further requirements in at least Texas is we have to ensure that the capacity has expansion capability to be able to serve into the future. And the hydraulic design has indeed included peak flow of domestic sewage, peak flow of industrial sewage, and any maximum infiltration weights that can be estimated. And the last one is a fairly important stipulation. And although this is taken from the Texas code, I feel comfortable in stating that some version of this statement would appear in any design guidance in the United States, if not in the world, certainly in the United States. A collection system must be designed to prevent surcharge in any pipe at the expected peak flow. So they have provided a design criteria that's pretty important, because that design criteria is going to directly impact the pipe dimension. Some further requirements are capacity analysis. In Texas, they've been nice enough to tell us what the minimum pipe size is, so we don't have to make a guess. So we start at 6 inches and work our way up. And 6 inches is undoubtedly selected, not just hydraulically, but that's the minimum size at which your average depleted fur teddy bear can be conveyed down a sewer to the treatment plant. So any smaller than that, you get teddy bears stuck, along with golf balls and other small stuffed animals that find their way into the toilet and out your system. And so they selected the minimum pipe diameter to be able to convey the largest blockage that they don't want to have to deal with. Connecting stormwater drains into a collection system is currently prohibited. In the past, 50 years ago, that may have been tolerated, but it's explicitly prohibited in the current design guidelines in Texas, and I again would say throughout the United States. The owner can use data from an existing collection system if it's available. In the absence of that data, the design should use data from a similar system or by the following design process, which is provided for in Texas codes. The sizing of pipe for new collection system must be based on engineering analysis. So that's saying a professional engineer has to be involved. And the design is sized for peak flow, which is based on estimated daily sewage flow as shown in figure 4. And the next slide is part of figure 4. And figure 4, as referenced in the prior paragraph, refers to a series of pages that look like this. So in this particular table, it's providing organic loadings and flows for new facilities based on different source types. So residential sources, 75 to 100 gallons per person per day are anticipated, and the wastewater strength is 200 to 350 BOD5, or 5-day biochemical oxygen demand. Mobile homes, slightly smaller flow rate, but slightly stronger wastewater strength. Schools, recreational parks, office buildings. So office buildings have higher wastewater strength. Don't know why. Hotels, high strength. And then when we get to restaurants and bars, the wastewater strength is greatly increased, presumably because of the lipids that are contributed from restaurants and the washing of dishes and leftover materials from the preparation of food. So restaurants waste a lot of protein. So there's a lot of protein materials that go down the drain, and that's reflected in this wastewater strength. Ironically, hospitals and nursing homes, which are notorious for having unpalatable food, basically have a wastewater strength that's 1/3 that of a restaurant. So if you want to get out of this engineering business and make your fortune in operating hospitals and nursing homes, put a good restaurant in either of those things, get that wastewater strength up, and you'll have happy customers. You'll be incurring other problems with that. So that was maybe not the bestest idea. So pretty much biochemical oxygen demand in the 350 milligrams per liter is typical, and there's more and more tables than this one presented here. So pretty much any facility you're likely to connect into your system has a direct representation in a table like this, or a description close enough that you could use that as a starting point. There's also many different equations, and I'm showing just a couple here. So similar to how we might have estimated drinking water demands by equivalent residential units, there's a similar approach provided for in the Texas Administrative Code. So here's one equation where discharge Q is equal to the per capita wastewater production in gallons per day, pretty much prior table, times 1 plus B, where B is the number of bedrooms. And so this would work per residential unit. So this one would be appropriate for somewhere USA, for instance, because that's a small enough study area that we've been using throughout the semester to practice some of these procedures. Pretty much 4-bedroom per house in the Somewhere USA thing, and then multiply by the number of connections. That would give you a pretty effective way to estimate wastewater discharge in gallons per day from that entire subdivision. Alternatively, there's another equation in the code that looks like this. This is Q is equal to a rate factor, the number of dwelling units served, and some kind of factor of safety. You look at these two equations. This is Q equals X times 1 plus B. This is Q equals A times N plus B. So mathematically, structure, they look the same, but the meanings of the letters are different. And more importantly, the flow units are different. So this equation's in gallons per day. This is gallons per minute. And there's yet another equation where the N is replaced with the letter P and A is replaced with the letter A sub 1. This happens to also be in gallons per minute. And the key point of showing you the three equations is these are okay to use. There's nothing wrong with them if they're appropriate for the design that you're considering. Pay very close attention to the units and don't mix equations. Don't use this one for some of it and then this one for a different part. I think you're just asking for a computational screw up, although these two are at least in gallons per minute. Other jurisdictions outside of Texas will have similar estimate guidelines, as will individual communities within Texas. So the Houston one, the Houston Infrastructure Design Manual is likely to be quite similar to those equations. Here I reiterate the note about the equations. The units of these equations, which have similar structure, are quite different. One produces estimates in gallons per day, while the other two are gallons per minute. Be sure of the units that you use. So don't select the equations willy-nilly. You probably don't need me to tell you that, but it doesn't kill us to remind ourselves. Because mixing them is not usually justified. So when we get to the point of having to do the hydraulic modeling, we already know how, because the collection system pretty much works the same way as a stormwater system. We can actually model it in SWIM. And SWIM, in my opinion, would be as good a modeling tool as any for checking the hydraulics of wastewater. Because the flows are actually somewhat confined, SWIM may even be overkill. We might be able to do a design akin to the rational method, although there's no rainfall runoff portion, to size our pipes and so on. We could also use SWIM to model flow through a treatment plant. It's relatively uncommon, but it could be done. It would take some modeling skill to replace reactors in a real treatment plant with rectangular channels of appropriate dimension, sumps as storage nodes with appropriate elevation and volume dimension, pumps are pumps. And this could be useful for computing hydraulic grade lines through a plant. The head losses between unit processes would take some trial and error in order to enter the head loss terms. It turns out that the SWIM computer program actually has input cells for specified head losses in different components of your drainage model. So SWIM was pre-built with this capability, although I don't think it was ever intended for treatment plants. That's just sort of a cool thing that it can do, that because the hydraulics doesn't change whether it's sewage or stormwater. And so now we'll close up with the definitions of inflow and infiltration. Inflow is defined as direct connections to sanitary sewers, and we'll look at some pictures of that in a second. And infiltration is leakage into sanitary sewers. So the key word here is infiltration is water that gets into the system because of leaks. So it's not supposed to get in. Inflow is water that gets into the system because there's a direct connection, and in that direct connection is an accident. So if we directly connect roof gutters, French drains, or German drains, or Swiss drains, or even lateral drains. So I was trying to make fun of that. These connections aren't supposed to be allowed. So these are undocumented or unauthorized connections into sanitary sewers. They happen in every community. It's not like the people that make the connections are out and out criminals. But they take flow from a roof gutter, and rather than run it across their yard, in some cases, it seems hydraulically easy, just connect it into the sanitary system. But that's technically illegal, and code enforcement could issue a citation if the owner is unwilling to break that connection. Infiltration, on the other hand, is even more nobody's fault. Pipes crack, especially if they're crack pipes, so that's almost funny. High water table, leaks that occur at joints, leaks at junction boxes, those all provide pathways for groundwater to get into the sanitary sewer system. When that water gets into the system, it dilutes the sewage. That's a good thing in one sense, but it increases the volumes that have to be managed by the sewer system. And over time, those added volumes from infiltration can overwhelm the capacity of the system. And so that's the main reason for focus on inflow and infiltration. Here we have a nice cartoon, and we will go ahead and identify inflows and infiltrations. So inflows, is, if you recall, are direct connections into the system. So here we have a roof drain that downspouts and makes its way into the sewer system. That's bad. Here we have a driveway drain. It too is connected into the system. And in this case, we have a foundation drain that direct connects. So the downspout, the driveway, foundation drain right here are all examples of inflow. Here we have some inside the house. We have seepage from the floor, goes into a floor drain, and that too is directly connected to the sewer system. Generally, that would be an unauthorized connection. Here we have a sump pump that also is going directly into the sewer system. So the sump pump for sure is an unauthorized connection, also a type of infiltration. The footer drain directly connected, and the sump pump they connected into the vent stack. That's actually pretty good. If you're going to do an illegal connection, that's actually kind of ingenious plumbing when you think of it. I wouldn't have thought to do that, and I've done a lot of amateur plumbing butchering. So those are most of our infiltration examples. If the viewport or the clean out cap had failed, there would be a direct connection that way. Infiltration is through faults in the system. So here we have a cracked, broken pipe and high groundwater, leaking or bad joints, water's getting into it, leaking or bad connection, we have water getting into it. Now there's a couple features in the picture where water is supposed to get to the sewer. The vanity drain is supposed to go into the sewer. The toilet is supposed to go into a sewer. That's the whole point of what they're there for. And the wash tub in the laundry room is supposed to go into the sewer. So this connection, and that connection are indeed authorized. Those are intended sewer connections. And so what we can see in the drawing, at least in this drawing, that there's 3 intended connections and a whole bunch of unintended ones. And collectively, the unintended ones combine to add additional volume to the system called inflow and infiltration. Here's another cartoon depicting the same kind of scheme. In this one, it's nicely color coded. So we have a roof drain, direct connection, so that's inflow, uncapped clean out, direct connection, so that's inflow, a stormwater cross connection, which is direct connection, that's inflow. And so these are holdovers from the old combined sewer system days. And in general, in most communities, there's been active programs to disconnect these from, to disconnect the crossover. So the storm sewer and the sanitary sewer stay separate. So the blue and orange don't mix. And here we have a faulty manhole ring, and that is our other direct connection. And then in terms of the faults in the system, the roots intruding into a lateral, a broken lateral that lets groundwater in, the connected foundation drain. So I would dispute the color coding that this is infiltration. I think that this particular one is more likely an inflow. Faulty lateral connections, so they didn't use the right amount of JB weld when they glued the two pipes together there, and that provided a pathway for water to get in. A crack pipe or a deteriorated vault box. So those last two pictures are examples of inflow and infiltration. And in the cartoons, they're shown pretty much at the house level, and you multiply that by the number of houses in a community, and you can probably convince yourself that there could be a substantial amount of flow during a storm. And that concludes today's presentation. It was a little shorter than usual, and that was intentional. Thursday, we'll look through a couple of design guidance documents to familiarize ourselves with the location of these various rules. Although this particular presentation has essentially summarized everything we'll find when we do that. And I will, if there are no further questions, I will go ahead and end today's lesson.
I've got a question. I know the Atomic Kitty stuff crashed down, and you had stuff loaded directly on Blackboard, but there's still a lot of some of the documents that you had set up from past lessons. I haven't been able to access those. All your PowerPoints are available, but a lot of like the secondary readings and resources you provided are dead links.
How long ago did you look?
It's been a couple of days.
Okay, so
pretty often, but a couple of days ago is the last time I checked. Probably Saturday.
So I noticed that that a lot of them were missing, and I just uploaded a bunch this afternoon. So I may have restored most of what was missing.
Okay.
And so take a look at that, and at the risk of making a fool out of myself, let's just go to one. So something like right in here. Check the notes. Okay, good. That one's still, so Werbs is W. That's way down in the alphabet. So that's one of the last ones. And the other one I was missing earlier today was wastewater collection systems was not there this morning. That's why I noticed something was wrong. So I think I've restored a lot of that functionality.
Okay, I'll go back and check that.
Okay.
One of them I was trying to get was lesson 5. I think there's like one of the documents you had for like a review material.
Okay, let me let's check that, because this is a good time to do that. Lesson 5, pipeline hydraulics, closed conduit. That one's there.
Okay, yeah.
Okay, I think they're all restored.
Okay, I'll check and see if I can.
The only thing that's not restored is this web tools. I mean, it goes to something, but none of them work right now.
Yeah,
because they're not there. But the remainder should be restored. But thank you for asking. I noticed that myself not too long ago, and one of the rare times I actually got it fixed ahead of time. So cool.
All right, thank you.
All right, anyone else? Well, very good. Expect another exercise to appear sometime in the next few days. It won't be a terrible surprise. It's going to be a detention pond will be the next thing, and then we are going to still do a drainage design for the Somewhere USA subdivision, and then there'll be a final exercise, or actually assemble all the stuff you've done on Somewhere USA in a report format to constitute the semester design project. So we're getting to the end. We're actually making pretty good progress in light of all the various challenges of online classes and your instructor's inability to keep an Amazon web server running, which you would think would be easy, but it's not. So with that, I will conclude the call for today, and I wish you all a great evening, and have a good day tomorrow, and I'll see you Thursday evening. And until then, take care, be careful, and so long.